Okay. I had to read the story. Okay. Once upon a time, Papyrus the skeleton went to buy some pasta from the store. The store's inventory is bare bones and they only sell one thing, boxes of uncooked spaghetti. The store always stocks exactly K boxes of pasta and each box is numbered sequentially from 1 to K. This box number also corresponds to the number of sticks of spaghetti in the box. Meaning the first box contains 1 stick, the second box contains 2 sticks, the third contains 3 sticks, and the K box contains K sticks. Because they only stock 1 box of each kind, the store has a tendency to sell out spaghetti. During each trip to the store, Papyrus likes to buy exactly N sticks of spaghetti by purchasing exactly B boxes, no more, no less. Not sure which boxes to purchase. Papyrus calls Sherlock Bones for help, but he is stumped. Do you have the guts to solve this puzzle? Given the values of N, K, and B for T trips to the store, determine which boxes Papyrus must purchase during each trip. For each trip, print a single line of B distant space separated integers. Knowing the box number of each box of spaghetti Papyrus purchases. Recall that the store only has 1 box of each kind. It is not possible to buy N sticks of spaghetti by purchasing B boxes print -1 instead. For example, Papyrus wants to purchase N equals 14 sticks of spaghetti and B equals 3 boxes, and the store has K equals 8 different box sizes. He can buy boxes of 842, 752, 761, and other combinations. Any of the combinations will work. The function description, complete the Bonetrousel function in the editor below. It should return an array of integers. Bonetrousel has the following parameters: and the integer number of sticks to buy, K, the integer number of box sizes the store carries, B, the integer number of boxes to buy. Input format, the first line contains a single integer T, the number of trips to the store. Each of the T lines contains 3 space separated integers N, K, and B. The number of sticks to buy, the number of boxes for sale, and the number of boxes to buy on this trip to the store. For each trip to the store, if there is no solution, print -1 on the new line. If there is a solution, print a single line of B distinct space separated integers, which each integer denotes the number of noodles in each box that Papyrus must purchase. If there are multiple possible solutions, you can print any one of them. Do not print any lead-in or trail-in spaces or extra new lines. Okay. The explanation is Papyrus makes the following trips to the store. He wants to buy exactly B equals 3 boxes of spaghetti and have a total number of N equals 12 sticks. During this trip, the store has 8 boxes of spaghetti sticks where the box has 1 stick to the second box has 2 sticks. And the third box has 3 sticks, and so on. One possible solution would be the following. Paris can buy the 2 stick, 3 stick, and 7 stick boxes for the total of 2 plus 3 plus 7, which is 12 sticks. Note that this is not the only valid solution. Other valid solutions are acceptable. He wants to buy exactly 3 boxes of spaghetti and have a total of 10 sticks. Because the store only has 3 boxes in stock containing 1, 2, and 3 sticks of spaghetti, it's not possible for Papyrus to buy N sticks of spaghetti, as buying all 3 boxes would only yield 1 plus 2 plus 3 equals 6. which is less than 10 that he wanted to purchase. Thus, we print -1 on a new line. The third and fourth trips to the store both contain the same values, n equals 9, k 10, b 2. This illustrates that there may be multiple solutions for a given trip to the store, and any valid solution is acceptable.
About your process, everyone.
My first thought is to clarify what's the in the function, or I mean the method that we're coding, what's the input we get and what's the output we want to create. Specifically for the method Bonetrousel. I could go ahead and say like what I think. So the input is n, which is the number of sticks we want to buy. It's K, we have k, the number of boxes in the store, and then b, the number of boxes we want to buy. And what's really important is k is not only like how many boxes are in the store, but also like each box in the store has a particular number of sticks, and it ranges from like 1 stick to 2 stick to 3 stick, all the way up to k sticks. And each box has like a unique number of k sticks, or unique number of sticks that can range from 1 to k. So there's no repeats. There's not like a 2-stick box and another 2-stick box. It's all unique. So that's the input. And something that like I really want to point out that can be confusing, we're dealing with the method Bonetrousel, and the output for Bonetrousel is actually going to be an array list. It's going to be a list. The problem keeps saying like print this, print that, but the printing only happens in the solution method. We're only editing Bonetrousel. You can like see in the Bonetrousel method, it says like right on the left of the name, it says list long. So that's what we want to output.
And T is a number of test cases, or a number of trips or test cases, or how many times, how many problems are.
Yeah, like how many trips, how many times you need to figure this out. Yeah. Yeah, you can see that in like the output, I mean the input examples, like in the description of the problem.
Yeah, 4 gives you 4 test cases or 4 trips.
Yeah. So that means like in the solution, we're gonna run this method Bonetrousel like 4 times. But within the Bonetrousel method, we don't have to deal with T. We don't have to deal with this. Yeah.
One thing I also noticed is that if you scroll back up, I believe that the order of the elements doesn't actually really matter, although it might perhaps hint like if there's a better way to select the elements. Like maybe it's better to start from one end or the other, perhaps. Just a thought.
So the other thing too was this example here, box sizes of N, B, and K. The way they had it here, where N is 14, K is 8, and B is 3, they show you 3 possible outputs, but I found another one, so it's 4, and I didn't run any more of them, but I'm not sure what the maximum is, but I found another one that wasn't shown here. So there is a lot more possible outcomes.
Yeah, it did say like these 3 arrays and more outcomes are possible. Yeah.
Yeah, so you can do as many times within the range of K. So if 1 to 8, you can make as many possible combinations of 14. You just need to You just need to pick out one of those possible choices.
And mainly it's just saying that it's, the main thing is that there's no repeating numbers, right? In your selection.
Correct, they're all unique.
Okay.
Yeah.
As long as you get a combination of unique numbers to equal to what you want, and you pick out what you want.
Mhm. Yeah.
Mm.
Before we keep going on, I want to like see if anybody has questions about like understanding this problem. Because there is something I want to point out too. This goes back to like our process, actually looking at the constraints and like really keeping them in mind. The first three aren't like too special. It's just saying like how big they can go. But when I was working on this problem, I noticed like the last constraint, B is less than or equal to K. I mean, like when we're still thinking of like our first approach, it might not be that helpful, but when we go deeper into it, it's good to know that we're never going to get a B that's bigger than K. So we're never going to want to buy more boxes than there are in the store. Yeah.
That's a good point. Keep in mind. It would also be not necessary if they gave us a K higher than B, because we would never buy any of the boxes higher than B. Or whatever our target is. Yeah.
Like if we want to buy 3 boxes, there's not going to be a box that has like 4 sticks. Right.
Yeah.
Wait, yeah. What? Well, actually, no. It says like B is
It'll be
less
less
than
than
equal to K. So
there's always going to be the chance to buy all 6. Yeah, we'll never be allowed to not buy all. So they're not going to say, oh, there's only 8 sticks, but you need there's only 8 boxes, but you need to buy 9 boxes.
yeah, that wouldn't
So they
happen.
would never say you need 9 boxes, but it's only K of 8. That's what they're saying now.
Yeah.
We'll never need more boxes than there are available. The question is whether or not they'll add. So the next step of the solution process.
And if there's any confusion, I think I realized that you can, so for different test cases or different trips to the store, you can use the same number in another test case, just not in the current test case.
Yeah, I noticed
As
that
you
they give you the same test case, but they give you 2 different results on
Mhm.
some of these.
Yeah, I saw that.
But it says there's multiple things, so it doesn't mean that what they give you for an answer means that that's the only answer. You could use a different answer as long as it meets the test case, as long as it meets the requirement.
Well, like Evan, what you were saying was like, yeah, actually, can you say what you were saying again?
Oh yeah, sure. I'll try to clarify it better this time. So like, for example, if you're buying on one trip to the store, like let's say you have 2 of the same test cases,
Mhm.
I think it'll still take the same solution for both of those trips, even if they're like the same inputs. But as you can see, like he can buy boxes of, oh wait, that's all one trip in that. You'll have to scroll down to the test cases.
Yeah, one of them was like 9, and you had to use 2, and one answer was 8 and 1, and the other one was like 5 and 4.
Yeah. Well, like what I first
Here's
interpreted, you were
Again, they
saying.
don't care
Here's an
what you
example, sorry.
actually send. Hold on. So what just to point out to you is that, and again, always be very careful with these things. Sample outputs aren't necessarily telling you what you have to give. They're just giving you examples of what is valid. They pointed out that they just want a valid set. And so they most likely have something in the system that will test whether or not what you outputted will fit the requirements. All the requirements are is the length of what you returned K. Not K, sorry, the length of what you returned equal to B. And are the items inside of it less than K less than or equal to k. So that means you're only picking boxes within the range of 1 to k, and are none of the numbers used twice. All those items are valid, and then the total of the items in the set equal to n, then it will accept that as a valid answer. So not all hacker ranks are looking for very specific outputs. They're just looking for an output that falls within a range of requirements. So do be aware that the hacker rank does have that system in place where the answers that you give aren't static numbers or static values. They can be a range of values. Where as long as you return one valid option, it's happy. Yep.
I had one idea though. One thought came to mind, like seeing that though, while yes, it'll accept any valid solution, any valid answer combination in this case. Perhaps there might be a better, what am I saying? Answer. I was going to say answer. No, a better combination to return that's more efficient.
But that's not
More
necessarily what we're
efficiently
looking for. Yeah. Because again, they're showing you that in that example right there. 9, 10, 2, 9, 10, 2. They would accept either 5, 4, 1, 8. And we can even go farther and say, oh, they would probably accept 2, 7, and 3, 6, and all those different variations of it. That's what they're trying. Would take into consideration they're trying to specifically show why else would they give you 2 of the same inputs but different outputs. You couldn't. I'm guarantee you can't give me any justification how you would be able to know that the third input or the third test was expecting you to return 5, 4, right? There's nothing to tell you why you should give that one. Well, the fourth one is expected to give blank.
Yeah.
This is one of those things that hacking does to try to make sure it's clear. We're not looking for specific answers. We're not looking for the best scenario or the least of worst scenario or anything like that. We're just looking for a valid.
Oh yeah, above the function description, it says about the outputs, it says any other combination, any of combinations will work. So it does say that it's not, these are etched in stone.
Could you I'm thinking though, could you reuse the same combination for if the 2 trips to the store are with the same inputs? So maybe we could reuse one of our computations.
Well, I would.
It's just an idea for now. I'm not going further with it yet.
Yeah, I see what you're thinking. That said, I think like it doesn't work like in the scenario like what we're solving here. So all we're doing is modifying the method Bonetrousel. So we're not going to have any memory between the trips.
Yep.
I see.
Good
Yeah.
point out there, Leroy. Yes, very good observation there. That's a very good observation. Yeah, the method, yeah, it's a one-time use.
Yeah, like you can see, we don't have like T in the parameters of the method Bonetrousel either. So what solution is effectively doing is it takes the first trip, runs our method with all the arguments and the parameters, and then it's going to do the next trip and then run our method, the next trip, run our method. Yeah.
Yeah.
Can I jump in real quick and just ask someone what the question is?
Good. Yes, please, John. Help make sure that people are following at least some sort of solution process. Good call.
Right. Right. And also for those who may not have spoken up yet, maybe just in their own words, or it doesn't have to be accurate. We're just building a concept of what the question is in our own words.
I mean, to me, it's straightforward. Question is, how many boxes do we need to buy per trip?
Oh, I like it.
And can we buy the amount of boxes needed per trip?
Right, right.
If not, return -1. Otherwise, return the boxes needed. Again, a very not scientific way of saying it at all, or coding way.
That's what I'm after personally. But there's one go ahead.
I wasn't too sure. I don't know if you guys have already answered this one or not. But like, so if you take a trip, you bought the boxes, right? Does that eliminate that amount of boxes from the store? So, or is it just like the number of boxes? It's just what the store has whenever you come back from a trip? Or,
I think each trip, because each time it gives us a new K that's the store contains, I'm assuming that that K is what the store contains each time. So the trips are their own individuals. They don't communicate or have any relationship with the other trips. And
but they still need to come up to a total of a number of sticks to buy.
per trip. Per
Okay.
trip has its own, like the N is the desired
Mhm.
number of sticks they want, and B is the limit to how many boxes we can purchase.
Okay.
And then K is the box sizes available, the number of box sizes available.
And K will change per trip.
All of them can change per trip. Yeah.
Oh,
Yeah.
okay.
Yep, they are all different inputs.
Oh,
They
okay.
can be, or they can be the same.
Yes.
Yeah.
Interesting.
You can also think that one trip is he did the first trip today and the next trip he did like next week, or the next trip he did like 2 months.
Oh, okay. It was just
You
the
know,
same.
yeah.
All right.
Mm.
Oh, that was the only thing, because I was trying
Hmm.
to get this over, because this is a interesting one.
Yeah, it is an interesting one because like there's so much to it. There's so much going on, obviously, with the game reference and everything. And then what's the question underneath all this? This is like how many
It's very
boxes?
wordy.
Very wordy. So it's helpful to know techniques to cut through all the wordiness and ask ourselves, what's the question? Like Alita said, what's the inputs and the outputs? Question is, like Christian said, how many boxes can we buy? And there's a caveat, right? Because the store only contains one box of each amount of spaghetti up to K. So
I would
it's a weird store like that.
I would add a tiny thing, just like change language to be more precise. Not how many boxes can we buy, but which boxes can we buy?
Look at it. Okay, which boxes can we buy? Yes.
And how many solutions are there per?
Don't need to know
Well,
that.
No.
Do
we
not
We don't need to
know
know that.
What?
We only
well,
need to give at least one solution, or like just one
Yeah.
of them.
no, I mean, how
We just
many different combinations can we make out of what we're given?
Ooh,
That
again,
doesn't.
We
Yeah.
don't need to know how many
Don't
different
need that.
combinations we could buy. We just need one valid combination. As long as we find one, we send it, we're done, right?
yeah,
It's
but
not
that's an
asking us
important.
how many combinations.
Right, but which one could we get to faster? How fast can we get
Doesn't
to
care.
that one versus the
That's
other
what I
ones?
was hinting at, but I think we're jumping a little ahead if we try
Yeah,
to
slow
figure
down a
that
little
out right now.
Jim, I will say that this is a really important part of the process, clarifying what the question is and rabbit holes. And yeah, it just asks for one combination of types of spaghetti boxes that we can get. I do the same thing. I answer like a totally different question. The question says, though, we need to return one list of longs, and that's going to be our one combination that we find. Right? Is that?
Yeah.
Mhm.
That's why I think the question part is the most important part of the whole thing. Because if you're off by a degree in this part, you're going to end up way far away once you get to the approach.
John, I have a question. So it's important to be able to articulate the question, but more in like human words rather than computer or sciencey.
I think so. Personally, I think so. I think people would agree. So, you know.
You can hold it in your head better too, that way.
Yeah, you can talk about it with others better.
Right. Otherwise, it might confuse the interviewer if you're not being too clear.
Yeah, well, yeah, they'll probably know the computer lingo too, but yeah, it just,
Be
Right.
technical during the interview, 100%. Use terms of art.
yeah.
You're usually, by the time you're doing a algorithm, someone, you're doing it with another developer. So definitely go along with the assumption that they do understand the terms of art. If they don't, they will ask you. So of course, use terms of art that you understand. Because yes, if you use one that either doesn't fit, or that the interviewer doesn't know, they'll ask you, wait, what does that mean? So make sure you're ready. Don't use a word you don't understand, of course, and only use the terms of art if it's the right term of art. So be careful on that, but 100%. Be technical. And if someone in the class, if you don't know that term of art, you should be asking. Don't be like, oh, they seem to know it. I'm not going to say anything. Understand that that when you think that, there's probably one or two other people that think the exact same thing. So ask that question, which looks like we got that. But Colin just said something. EL15. Oh yeah. Explain like I'm 5. Okay, yeah. ELI 5. Ah. So yeah.
Yeah.
Technical terms of art, but keeping it simple. But once yes, if someone doesn't understand it, ask them, and then you break it down to a more simpler concept. So use terms of art during the interview, but be ready that you might get told, explain that deeper, explain more. So be ready for that. But yeah, don't be afraid of terms of art. Make sure everyone understands it. If you hear a term of art, you don't understand it, ask, because again, that can, one, it helps you learn that term of art for your interview, and two, it might open up other people who didn't think of how the term, maybe they would think of the term of art in a different way. It could open up the idea of how to solve the problem. It could give you other ways of solving the problem because then you explained it in a little more detail. So using good terms of art, so you don't want to be explaining to your interviewer like they're 5, because then they're going to get annoyed with you. But you do want to make sure that if you do use that, when they do ask you to explain what you're saying, it's simple. You can't.
Okay.
So have we come to a consensus on the question?
Can I try to say this in a not spaghetti way?
Joe?
Way or fettuccine.
100%. No one says you have to use the terms in the story. Again, one of the techniques I think we talked about is extracting what's important and what isn't important, and removing what's not important. Getting rid of the fluff of the story.
So you're gonna get input. You're gonna run through this thing 4 times, number of times, which is for this sample is 4, which is what? Is that T?
Yes.
So we're gonna run through this thing 4 times, and we're gonna get an input as numbers, and it's gonna come in sets of 3. The first number is the total of all the numbers. Is that right? First number is the
Goal.
total.
We can call it the goal.
The goal, okay. And what's that second column?
It is
The
K.
largest option.
It's K. Oh, it's the largest number. So it's because we're gonna have it's gonna be I'm thinking this is starting as an array from 1 to K. Is that correct? Do you think that's correct? Is it
So to
is
speak,
sequential?
no one creates the array, but you can imagine there is one, I guess, would be a safe way to that. There, you have all boxes, or you have all options from 1 up to that second number.
Yeah, okay. So there's only one of each. So
Yeah,
that's
there is
the
no
second
actual
number.
array, but you can visualize it.
That's your maximum, that's the maximum number of we can call it boxes, and each box has that number of things in it. And we're gonna go, we want 3 boxes. We want 3 out of that K number that adds up to N.
You
So it's
got
like-
it. You got it. Yeah.
And I just need a second to write that down. That's like N, B, and it's N. This is total. And then B is and this is all right. All right, thank you.
All right, so that should set the stage for the next part. At least in my process, it's making observations. about question, you know, we went over the inputs. We know what we need to get. But what happens in between? How can we look at this different ways?
I do remind everybody from Tuesday, we learned that you all have access to annotation now, so make sure to take advantage of that today. If you want. No one says you have to, but we did find that out on Tuesday that everyone in the class can do annotation. As
It's
long as
fun
no
to
one uses
practice
it.
too. It's an acquired skill, so writing numbers with your mouse is not easy, but you get the hang of it. It can be fun.
What I say
Somebody-
is that you usually gain the ability to no longer be embarrassed by how bad you are.
Yeah, there you go.
Taking someone has to constantly write, and yet I still cannot draw good numbers for the life of me. You just
I-
learn to be okay.
I have a touchscreen, so I could just draw with my finger.
Oh, no fair.
Cheater.
Who wants to have the honor of running through one test case and with their annotation?
I'll do it.
All right, Evan.
All right, so here as our input, we have 12, 8, and 3. That is N. Oh, they chose yellow. Okay.
I'm gonna be really mean and ask you to write out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. An array, because that'll
He
be
wouldn't write that many. He would only write up to 8 because we only have K is 8. He
oh,
wouldn't
okay.
write
So K is 8, so you don't have to do 12.
So you can actually just type it out with the keyboard.
Oh, there you go too.
Oh, that's true.
Evan's going for it though. He's already at 5.
This is easier. And if you know what this is basically 1, 2.
I was gonna say.
Is it 8
really,
actually? Hang on.
That change the theme buttons.
Yeah, 1 to K.
Dark mode for his yellow.
Yeah, there you go. That was better.
Is that? No, I can't drag it.
Can't drag it.
It's
so
part of the
fun.
learning process. It's ugly, but
Yeah, you can't drag it.
it works.
Okay.
I do want to clarify, I would actually remove the array brackets because remember, we don't actually have an array. You're building that as a way of representing what we know. Remember, there's no actual array of K. It's just K of 8. And so we know that means there's one.
Oops, oh no, I erased it. Sorry.
Try to get rid of everything. I just said the array bracket. Jeez.
All right, I'll pull it up fast.
Yeah, I guess technically we don't need to build the array, but sometimes it
Here, I'll
helps.
go ahead and do those numbers. Oh, you got it there.
1, 2, 3, 4, 5, 6, 7, 8.
Yeah, we don't actually have an array. We just assume that there's a collection of 1 through K. We know that in our head.
And then we need to find 3. I need to actually look at this because I keep forgetting which is which. Is it N, K, B? So B is the boxes we want to purchase, and this is the sticks we need. And K is the number of boxes. Did I do that right?
And then write somewhere our goal. What's our goal somewhere?
Yes. Okay, I did that right. All right. Oh, our goal.
Yeah. What are we targeting? We want 3 boxes. We have 1 through 8. But what's our target?
Well,
12.
you want 12 sticks.
Give us an N
N
equals
equals
12. Yeah.
12. Can everyone see that? And B equals 3. So we need to get 3 boxes that sum up to 12. Forget sticks. Okay. So they pick a possible solution. Actually, I'll give a solution that they don't provide. Well, I'll just do it solve it as a human first.
Solve it the way you would solve it. Don't try to go out of any sort of fancy ways to get a number they didn't give or a solution they didn't give. Just solve it the way you would solve it. So everybody here, think of it. Now that you see the visual, go ahead and then give it like a minute. Just think about how you would approach this. All right. You can use whatever mental gymnastics you want to use. These are sticks of spaghetti. These are pairs of socks that are bundled together. Whatever, these are units of items. So none of these spaghetti sticks will be just units of items that are bundled together. However, it helps you to think of it, just so that, and think for 2 seconds. If you were now looking at this shelf of these items, how would you pick them out? So think for like a minute. And go on. And then yeah, keep going with your visual. But yeah, think you're thinking yourself and think. If you were at a store and this is what you saw, how would you grab three bundles to get 12 units?
Hmm. So that means I equal 12. Okay. I'm trying to solve this as a human would, right?
You should just start.
Okay. So I try to pick which 3 boxes, probably starting from one side, then moving through left to right. See, and then check if these add up to 12 to n, and if they don't, then pick 3 others.
Yeah. That's how I
Like
did it.
2 plus 3 plus 4. This is just, and this isn't even a great solution, but
Again, hold on a second. Don't treat those numbers like an array. You don't have an array, so you wouldn't be iterating through those numbers. Remember that. You don't have an array. You can build one, I guess, technically, sure.
Yeah.
But make sure again, to
3 plus
not
4,
treat
does
those
this
numbers like
equals 11, so that's not going to give us it. So that's 6. If we do 6 though, but 2 plus 4 plus 6 gives us 12. Does everyone see that?
Yeah, I'm actually interested to know how people in their heads solve this and like the idiosyncratic ways that people went about it. I'm sure my way is really weird. If I chose 2 numbers and saw if the remainder was in there, if there was a number that wasn't in the 2 that I already had to
Does someone
make
else
up
have
the
another
difference.
way they come through it?
I added 8 and 4 to get 12, and then I split the 4 to 3 and 1.
Look at that.
It's very not logical.
That's great though. Yeah.
Sorry. I was thinking of maybe dividing 8 by 3, but it doesn't give us a whole number though.
It's interesting though.
But of course, there aren't going to be 3 exact numbers that divide evenly into it, so you're going to have to find a number slightly smaller or slightly bigger.
Interesting.
I mean, I would think of it's like an aisle where the lowest one is on the first thing and then the highest one is at the end. So I would just go down and start working that way.
Interesting. Keep going with that one.
I mean, I know it's not an array, but I would say that it would be like the lowest is on the closest to the front of the store to the highest to the end, or vice versa.
Okay. So what does that look? What are the right questions to ask?
Like Colin
So
use
do you need
modulo.
Modulo. What's
Cullen said that in the chat using percent. I'm not sure if that's modulo or using percentage.
explain like that? Yeah. Okay, use modulo. Okay. More on that one. But Jim, so you're saying that you know that the low ones are on one end. If we did make an array and this was an actual store and there was all these boxes in front of us, at one end that they're low and one end they're high. Where can we go from there?
Well, that way you could actually, if you had to get to there, you have to get to the number. If you had to get to n the highest, you might as well start with the highest number and then kind of work your way backwards. So
interesting.
because, you know, you want to get there quicker.
Okay.
Oh,
Take another
I
pass
have
at that.
something. I have a slightly different, like, yeah, I would build off the idea of taking one from the lowest and the highest, seeing what they sum up to, and then subtracting the sum we want from the difference of those, and then see if we have a number of that. And if we do, we have our 3 boxes.
I feel like
So I
those
would
are
pick, so I would pick 1 and 8 because those are the lowest and the highest. Then subtract them from n, the sum of those two.
interesting. I hope you're writing this down.
Now, the other thing I was doing here when I was trying to solve this, I was adding all the numbers up from 1 through K,
Okay.
all of them up, because if they don't add all the way up, you're just going to hit -1. You're just going to say, I can't make this. So why
Why do you- Interesting.
trying to find combinations when you don't, when you can't make the combination in the first place? You're like, well, I can't make it. I'm out of here.
Yeah, I think you're spot on. Explain that to us again, though.
You can like add up 1 through K, whatever what the number is.
So
And
you're saying all the boxes in the store.
all the boxes in the store, add up all the boxes to see if it is possible to get N. If
Okay.
it is, then you can stop breaking that down. If it isn't, you can just say -1, or you could just say, I'm done. This is impossible for me to get what I'm
Oh.
requiring.
Wait, why is it impossible?
Because it doesn't meet up to N. If it doesn't equal N, if all these numbers don't add up at least till N, then you know that you can't possibly buy anything in the store. So if N was higher than,
Wait, because they don't have enough spaghetti?
yeah,
Oh my gosh.
because it's possible not having enough spaghetti to buy. So you could easily rule that as being a case.
Interesting. Anybody have a mathematical way to say that, or do people understand what Jim's getting at?
I do. Like,
Okay.
yeah, you just,
Mm.
yeah. Like, let's say, like, if we had an array of all the boxes, you'd like add up the entire array and then say, like, if this entire sum of the array is less than the n, the amount of sticks we want, then yeah, just return a -1. And even if we don't do an array, we could do some kind of method where it'd be like a recursion thing, where it'd be like 8 plus 8 minus 1.
What's that called? What's that called?
Factor?
Factorial.
Yeah, factorial. Yeah.
Yeah, factorial.
It's not factorial. Factorial is multiplication.
Yeah, factorial is multiplication, the exclamation point.
Oh, am I wrong?
I knew you were going to, I think you think of factorial. It's not.
Oh shit! It's not factorial. What is it
That's not
then?
factorial.
I'm wrong.
I don't know if there's a word for it.
Mm.
I'm sure the word
There
for it,
is-
I don't
there is
know-
not a word
I don't
for
know
it?
the phrase. I don't know if there is, but I know what you're thinking of. But it's
I missed-
factorial.
I missed on that
addition
one.
Instead of multiplication. Yeah, it is factorial, just addition instead of multiplication.
Mhm.
Is what you're pointing out. But again, but I do have to ask a question on
Oh, I
that.
see.
Is there really going to be a faster way to determine versus attempting to pick boxes and realize we just can't get that solution? Can we rule out the process without having to touch every single potential box? Because what's the maximum K we can have?
Maximum K, 10 to the 18th.
And what is that number?
That is a really big number.
Yeah, it is.
That's
So
why you don't want to
trying to
use
find out your-
pointers to solve this.
Yeah.
Well, N and K could be.
You would need n pointers, or rather K pointers.
Well, it shows N and K could be equal.
Sorry,
It
what?
can be.
N and K could be equal. Because it's 1 less than less than equal N K and 10.
Yeah, it could be, but I'm just saying that K, and so what you were thinking about adding up all the
That
boxes
makes sense.
together, we could
No.
have 10 to the 18 boxes.
Yeah,
You're trying to add up from 1 up to 10 to the 18 it's a long, it's just,
Yeah.
our computer would die. Just for the fun of it, you know what? Emilio, open another tab and just do 10. And then the caret symbol, which is the 6th number. So 10, shift 6, yep, and then 18. Enter.
Yeah, they don't even
Thanks
show
for
you.
that.
Oh, I was thinking about that. It was like a series or sequence.
Can we tell it to write that out naturally and not show it in the scientific form?
1E plus 18. What is that?
I'll do.
I mean, you could look at the
Oh, that's just
Wikipedia.
one. Isn't that just 1 to the E plus 18? Oh, no. Oh, never
Yes.
mind. 1
Yeah,
to the
it's
E
one.
plus 18.
No,
It's
it's
zeros, isn't it?
it's 17 zeros plus 1, I thought.
Oh,
Oh,
yeah, I think so. Yeah. I think
oh
you're
yeah,
right.
that's a,
And-
that would go way right up. That's huge.
Hmm.
So yeah.
Yeah, I don't think we can iterate through from 1 to that number and add them all together. I think our computer might die before it gets through all those numbers. What do you
Or
think?
computer.
Yeah,
Mhm.
it'll time out.
I think we would time out. That's a lot of numbers. Just trying to get through. You're into the quadrillions, and I think it is like we got 100,000, million, billion, trillion. Is that quadrillion? I think it's quadrillion. So I wouldn't recommend that. I wanted to point out that that's not going to be a faster method of ruling out an item, just to save us from that pitfall. That's one of those things, like I said before, be careful of those pitfalls. That's a major one right there. Thinking we can add those up because we're only looking at small numbers in our sample cases, and again, missing out on our constraints. Be very careful on those things. 10 to the 18 is a huge number. All right, we can go back to the code now. We're back to
Yeah, I don't think anything we've come up with so far is gonna accomplish that yet. Not the smallest and largest.
I want to hear someone else's approach again. So here, let me make this a little interesting visually. So we have, again, we want 12 items. We have 1, 2, 3, 4, 5. Let me actually visualize that better. 5, 6, 7, and 8. My goal for this is hopefully to help you guys stop looking at it as an array and look at it more as a human. So those are our spaghetti sticks in a box. Yes, I had one spaghetti stick cross over them, but it makes it easily more visible to see. So looking at this, how would you think to approach it? What would you start with?
Well,
I would start with go ahead.
Good one.
right.
Okay, I'll say I would start with the biggest one. Why would I want to pick the smallest one?
Makes sense to me. So we'll just circle the one we took. Where'd my annotate go? Okay, bring it back. Thank you. We took this one. What does that do to our goal though? Or what does that do to our, if you really want to think about it, to our end goal of 12, our B of 3. So when we take a box, what happens?
You're gonna subtract the 1 from the B because you need to take 3 boxes.
We need 2 more boxes, right? And what's our N now?
N would be 8 minus 12, which 4?
12
4.
And so now we have a much simpler problem ahead of ourselves, right? We now have, we need a number, we need 4, we have 2, and we now know, if we really want to be argumentative, we could say our K is now 7, right? Because now we have boxes 1 through 7, right?
Yeah.
Oh, yeah.
Interesting approach, right? I'm gonna do that. You guys keep talking about this now. Take that and go with it.
I mean, like
Or-
I had another approach. I don't know if my idea is what you're maybe hinting towards. But instead of starting from the highest number, I was thinking of starting with like the lowest, like the lowest combination you could have, and then like build on that with constraints. So I'll use like annotations for this.
I'm curious.
Yeah, so like in this scenario, we have 3 bags, right?
Mhm.
So for that,
Again, I'm gonna keep yelling at you, people, don't use array syntax unless you're planning to build an array. I
yep,
wouldn't recommend it,
right, yeah, yeah, it's just like,
because arrays make us think like, oh, we gotta do iteration, so.
I mean, like my idea was like using iteration, but anyway, so we
Okay,
have,
go ahead. Again, if your system relies on array iteration, then go ahead and use the syntax. I just make sure that if you're not going to use array iteration, then don't use array syntax.
okay, I think it like should work with that. Anyway, so doing it over here. So we have 3 bags, and so, okay, ignore the numbers for now. We have 3 bags, so I'd make a array with 3 places, and I want to first like populate it with the like smallest boxes. And then my approach is to like add on to each box, and like kind of grow it until it becomes like the goal that we're looking for. So like in this scenario, I would change it 3 to 4. I mean, like, so with 1, 2, 3, it adds up to 6, but we want 12. So then I would increase 3 to 4. That means the sum right now is 7. And then I would go here, make 2 to 3. That would make the sum to 8. And then make 1 to 2, makes the sum to 9. And then like go to the back again, make it 5, goes up to 10, and like so on. If I just continue
This looks
going.
very similar to what Evan was kind of doing, it looks like. In a way. Keeping the numbers kind of close to each other. The only condition, so I'm going to throw this out there though, again, what if our goal is 1 billion?
So
and our K is at like a million. So we
what
have
else?
a million boxes, yet you start at 1, 2, 3.
So what I was thinking with that, I don't know if this would solve the like time
Right.
problem, because like, so instead of saying like, okay, the sum of this, like you'd start with the sum, you'd start like saying, hey, let's find the sum of this entire array, it's 6. And then you would store that in like, okay, I'm getting into code, but like you would store it, and then just every time you kind of iterate or you add on to these numbers, you do like the plus syntax, you just increase this by 1. You're not doing a sum of this array every single time. But I don't know if that's enough to.
Kind of, again, you're still doing, in that system alone, you did, I think it's 6 permutations.
Right.
Alone.
Yeah.
And so again, my mention here again is that idea of, again, let's say that our n, the goal we're trying to hit, n, is 1 billion. You want 1 billion spaghettis.
Right.
And our k, the number of boxes we have, is let's say 50 million. I know that I can get a billion out of when my boxes can go up to 50 million. Because I can grab a couple of the high 50 million boxes and then just grab the small ones later. If you start on the low hand, it's going to take a while, right? And I got to wonder if you guys were at a bin full of, let's say, just a bundle of socks, various bundles of socks, and you wanted a certain number of socks for whatever reason, who cares why? But you want a certain number of socks, but all the bundles are the same price. So the price per sock is the same price. I don't see you guys just grabbing 20 individual, like 20 single socks. I always see everyone, I'm personally feeling like you guys are gonna grab the larger set first. I'm gonna try to find the largest kit first to minimize the number of boxes you have to grab, right?
Yeah, actually that makes total sense. Yeah, it would take forever to start with the smallest numbers and then just like add up until the billion. So I get that.
Yeah.
So can you do two ways about this? I agree with your approach of starting with the largest number first, but the other question was, can you divide and conquer? Like basically start with the largest and go to halfway and see if you can go in either direction and then continue to split until you can get to the number you're getting to.
It's possible. It's just you got to wonder though, by going straight to the middle, could you end up losing one of the higher numbers that you may need?
Well, if it's too low, then you can always go up and then still split up or split down to be able to see where the numbers lie, to be able to figure out where they go.
again, I'm always looking at this, why not always just grab the largest one you can grab, right?
Well, that's what I was saying. That's what I was thinking. You always want the largest one first, and then, but then where you go for the next one, if you can just eliminate a bunch of numbers and go down to the middle to see where you are at that point, then you can eliminate a bunch of, you can go through it quicker to figure out where that belongs. Because like I said, if it's a huge number, like you said, if it's like 10 billion, you're not going to go through every single one of them. But if I go down to 50,000 or so, is that am I closer to where I'm at, where I need to be? Or how far am I off in each direction?
You're throwing up a good point. So in this example here, yeah, we got lucky that by our system here, what is it? Let me manage it again. So in the example here, yeah, we only needed 3 boxes. So we grabbed the 8, we need 4, we have 2 boxes left. We know we shouldn't grab the 4 box because we need another box, right? We shouldn't grab the 4. We as humans know, I need 2 more. I can't grab the 4 box, even though the 4 box is available because I need 2. But as a human, I can be like, oh, I can take the next lowest 3 and 1 because there's only 2 boxes I need left. But what if we needed 12 gold, but our target was to do 3 more boxes? What if our target was 4? So we had the same thing, 12, 8, and then 4 boxes. We wanted to get our goal of 12 with 4 boxes. Well, if we grab 8 right away, that puts us as 4 with, again, 3. So we need to make sure we can prioritize this, right? And make sure we're grabbing right. So maybe you might be on a path there, maybe like, oh, well, do we always grab the middle of what we need until we only need 2 boxes left? Could that be an argument? And so these are the questions you want to ask. So what I'm trying to do for you guys is make sure you're asking these very human questions and looking at potential pitfalls, potential items like we see here. Yeah, this example looks great, but and always just make slight changes to the, once you find a potential valid solution, challenge that solution. Make small changes to your test cases, right? So based on what you said, maybe it's right that maybe instead of grabbing the biggest one, we grab the middle one. Well, we need a goal of 12, or maybe what you're saying actually, yeah, after we grab the largest one, maybe we got the middle one. Again, this is something I want to work out. It definitely feels like we should be working from top down or middle down or middle, not from the bottom, because we have such large numbers. If you start from the bottom and go from 1 up, incrementing by 1 at a time, we will come out. Even the other side, going from the top and going down 1 by 1 is going to be a problem. We need to make sure we're making big jumps every time we make a decision, right? So that's something to consider. So again, keep playing with it. I'm going to need my assistant at that. She's working on it. I want to make sure one thing I want to make sure is avoid that issue with the starting from the 1, 2, and 3, and working up from that. Yeah, we have quadrillion numbers. Yeah, it's going to time out. I just wanted to help you guys avoid that pitfall. Again, that's one of the ones you got to keep an eye open for, those types of constraints.
Cliff, are you playing with like hockey pucks over there?
Am I doing?
It sounds.
Oh, I found my
Fidget. Yep. Okay. Keep it off the table, but otherwise have fun.
The other headphones on the table. That's why. My bad.
Interesting.
Because I didn't even hear it. I'm like, what? That's not that loud. How's he hearing it? Oh, because the other earpiece is on the table.
Great.
That doesn't help. My bad.
Good.
That must have been annoying. That's great. That's on the recording.
A little bit, but
so
I caved and said something.
Can I jump in?
Do that.
Can I jump in
Go ahead,
about
John.
process?
Yes,
Just about the overall process. I feel like it's so awesome that everybody is developing approaches, and I would like to believe that's from a solid understanding of the question why so many good approaches are arising. But we're still on the observation step, and we should remember that by just noting the facts that we encounter and holding off on formulating an approach too early, because there are possibly many good ones. And I think Cliff was hinting at there is, there's one that's gonna be ultimate, so yeah. So what do we know? What do we know so far?
We know that we do not want to iterate.
Okay, there you go. I like it.
Because it'll
At least not iterate from the bottom up.
no, not like that.
Have the same problem though from the top down. If K was really high, but n was like really low.
Right, it's the thing, we wanna make sure we can jump around a little more.
Yeah.
100%. So yeah, we definitely shouldn't be starting high if if our goal is low, but our K is high, we wanna make sure we can notice that and jump down to N then. But if our N is below K, then that should be a one-step item, pretty much,
Yeah.
almost. No, we still need a certain number of boxes. No.
Yeah, and then Jim and Alita were totally on it. Everybody was totally on it, figuring out that if you have all B at the beginning, that's your lowest number, and if you have all B at the end, that's your highest number. So there's a fact. If we chose all the boxes at the end, that would be the maximum number we could get by selecting B. And if we chose them all at the other end, okay, that's one fact. Again, it's observations. Don't try to do anything with it. That's just there. Observe.
I'm gonna clear out my drawings. If you guys want something similar to that, you can put it back in. I'm gonna clear mine to clean
But
up a little.
But I would go back to saying that should we first should determine if we can actually get something out of the store,
Okay, fair enough.
because
Fair
we could
enough.
we can go through all this computation and we find out we can't. So it should be a way of determining, can we make a combination that will be that we can walk out with.
That's good. That's good. That's an observation. If the maximum amount we can produce is still lower than n, then we just exit out. After that, we still have to do our thing.
Oh yeah.
Yeah. Like another thing that pops into my mind, what are we doing? Colin posted for me summation, and we're adding all these different boxes together to equal n, and they have to be different numbers. So there's going to be this combination of numbers that equals n. They have to be different. It seems really simple, but maybe there's something there. We're simply adding together different numbers, unique numbers to get n. Flip was hinting at a process to find those numbers without iterating through all of them.
Is there a way of using division and dividing B into n to see?
I like where your head's at, to see.
Yeah, to see if it's. I'm kind of like what kind of words to put into it to see if it's divisible, or I'm a little lost. But if I used B to divide into n or use the two numbers in a mathematical multiply, I don't know, just use those two numbers initially to determine how to approach an outcome.
Interesting.
Like k divided by n.
And what would that tell us? What is k divided by n?
Well, it's not always a whole number.
Okay, but k is the biggest number of spaghetti box, and n is the amount we need. So if we divide the biggest spaghetti box by the amount we need, then we got.
Was it n divided by k? Did I get it backwards?
What are we looking? What's our target? What are we looking for in doing that?
Yeah,
Whatever numbers we end up dividing together, adding.
Yeah, backwards. It's the other
We're
way.
trying to find some kind of optimal place to start, or a number that's going to be included, or the top number of the combination, or the bottom number of the combination.
Okay.
Because we should be able to use all three numbers to some degree in some mathematical way to determine something, I would think.
Right? Me too.
Finding what that is.
Yeah, right. We're still brainstorming, right? We're getting there.
Yeah.
Is it n divided by k or n divided by b?
I saw B there, that's why I was like thinking B because it's there. I didn't see the K, so.
Should I
What?
make it b?
I'm thinking, yeah, like n divided by b because n is the number of noodles or like sticks we want divided by the bags we want.
There we go. N divided by the number of boxes we need. I see. Yep. Guess we need like an example, like a large number, like maybe is 1,000 kind of big?
Yeah.
Or yeah, let's just do a simple small number. Divided by, well, let's say 100 boxes. Oh no, this one's perfect. This one is evenly divisible. But what if we had 1,000 divided by 99?
Oh.
It's possible though.
Trying to think about what we're looking for more. The way I understand it, we're looking for where to start, and then we're looking where to start, right?
Yeah. Okay, divided by b. So this would equal 10.
Well, actually, so
That's a really ugly arrow.
my like thought looking at this is, yeah, like when we do n divided by b and we get say like a whole number like that, 10, oh, it is 10. Like my first thought is that like we'll have like the
Maybe more
box that
evil
has,
than this. Change this to a
thing.
1.
sorry,
I think you're just mumbling something about the drawing. Go ahead.
Oh, I just changed. I just was like, I'm gonna be more evil about this and change to 99 because that's too close to 100 to 91.
oh yeah, we want to get something that isn't like a whole number. Like in that example where we get 10 as the whole number, I'm thinking like we could approach it as like we have the box that has 10 sticks, and then the other boxes that we buy are going to be like 11, then 9, then 12, and then 8, and then 13, and then 7. Maybe like do it like that until you get to like 1, and then you just add on to the bigger ones. Wait, no, that never mind actually.
So it was like an amendment to your solution, but finding a better starting point. It's not bad. Could get you there quicker.
Then again, like I like the symmetry of it and like spreading out, but then I'm thinking like, wait, we have to add all this together to make it add up to our goal. I don't know if that does it.
Thinking like, how does this 10 help us? It gives us one number, true, but
It's, I guess like it's like if the store didn't have like unique numbers for each box, it's like if you went to a normal store and it had like boxes with all types of stick numbers, as many of them as you want. Like,
yeah,
what this is saying is that like I want 1,000 sticks and I want 100 boxes. I'm gonna buy 100 boxes, and each of them is gonna have 10 sticks.
right.
10 is
Yeah.
it. If you divided it evenly, you'd buy 100 boxes of 10 sticks. But we can't do that, so we instead do something else. Yeah.
Right. So you're saying by knowing that number, you got a pretty good starting point
Yeah.
because you're going to be kind of around that number. Yeah.
all right, yeah, I see that.
Interesting. Let's not get too attached to it, though. Let's not get too attached to an idea, but that's just a fact. It's an
Definitely gotta
observation.
go higher than that though. Oh no, wait, not necessarily. No, never mind. We might need some lower ones too.
What if we wanted to know the highest number we could include?
Oh no, wait, no, oops. No, you're gonna have to go higher because you need 100 boxes. Never mind.
Don't get too attached to the idea. How can we figure out what's the highest possible box we could include?
figure out.
So what's that install?
Minus number.
Right, if n equals 12 and b equals 3, then
You can subtract it.
interesting. What do you mean?
If you subtract 12 minus 3, then you get,
I'm in class. I can't talk to you. I'm in class. I can't talk to you.
I didn't know I butt dialed. I'm sorry.
We heard that.
Sorry.
That was funny. But yes, Jeremy, you're right. I think you're spot on. Is everybody else seeing that?
Oh, n minus b.
Yeah, n minus b is the highest number you can include. Is that true?
well, for this one it isn't, because the highest we can go is 8, because k is 8 and 12 minus 3 is 9.
It's
So-
warmer, but it's not quite there.
Okay, it's off by 1 though. It's close enough to be something.
Yeah,
Does it work with?
Hmm.
Does it work
But-
with other numbers? Like if n was 10 and
10 and
equal
3,
to-
10 and 3.
prefer that you go in the lobby if it's still open.
we're talking to everybody's contacts today.
I wouldn't go to the drive-through.
So
Oh.
if we took 1000 minus 100, but that's definitely way too high still.
Yeah,
So
that'd be 900.
what's b? So b would be 100 and n would be 1000.
That's what I put. Actually, does that fit our constraints? I think it does.
Yeah, it does. So if that was the case, then our biggest box could be 900.
Actually, no, McDonald's doesn't see the name, I don't think. McDonald's you need to-
Oh, you're right. I think
And that
so.
and the other
No,
9
wait.
could be
Everywhere else.
I don't know, like
Actually, never mind. No,
let me write this out.
it might be. It might be.
I mean, is that
Yeah,
true?
actually,
Is
no,
that true that n minus b? So b plus n minus b plus 1, where b plus 1 is bracketed. That'd be 899.
Actually, in this case, yeah, 900 would work. And then you would just choose smaller numbers.
Yeah. So that's another fact, maybe. N minus b is biggest number you can put in combo. Right now, I'm still considering it to be an assumption, but I think I'm erring on the side of this is true. N minus b is the biggest number you can put in combo.
Why do you think that again? Like I don't see how that would be the highest number.
Well, because it worked for that one test case, and it seems to like
Does-
make gut sense. Maybe it's not exactly that, but it's something around that.
Test case, the like what was it? The well, I might have zoned out.
Right?
It does seem to work. Like even with n equals 12, like it gives you 9, then you see if you add 2 and 1, you get 12.
Okay.
And it did work with 1000 divided by 100.
Yeah, so there's something there, I think, that could. And then
But let's challenge that theory. What
yeah,
about,
challenge it.
what about a higher minus like 900?
Okay, so b is 900
Yep. N
And
is
K.
1000. Then we have
And-
100 as our
and
max.
k is 1000. So that would be 100 is the biggest number that you could include in that. Wait,
that-
that doesn't. No.
Oh wait, I
Wait.
think this is invalid technically, maybe. Oh wait. I mean, they're
But see-
valid inputs, but they may still be an invalid.
There must be something wrong with it then.
So it wouldn't work for the example to the left here, where n is 14, b equals 3, and k equals 8, because 14 minus 3 is 11. But if it's beyond it, we could just assume, we could just say bring it to the highest number, equal to k, because k is the highest it can go. So we would reduce it to k, and then go from there. Because
Wait,
14 minus 3 is 11. We can't use 11, but we can.
why could, oh, right. Yeah, I see
And
what
we
you're saying.
could say that we could use k because k is the highest. So we could just say, if it's beyond that, you start with k and then work our way backwards, or work our way from there.
Okay, so there you go. So if n minus b is greater than k, then k is the biggest number that could be included, given that there is a valid solution,
Right.
which we would have to check by collecting all the last b, the biggest b's.
Yeah. So the second one on the sample input, where it's 10, 3, 3, 10 minus 3 is 7. So that would just, that's a -1. So it can't be done anyways. But the whole fact is that 7 is way beyond 3.
I'm wondering if there's anything there, or if it needs some tweaking, the n minus b thing. Anybody have some other angles, some interesting facts that could help us? Cliff, are we gonna get to approach today?
I'm not so sure. Like, I'm trying to follow what you guys are looking at, and like, I saw the division thing, and I thought that it had potential. So I was looking at that as a potential area. Again, it's how I get this working. Again, it's mostly just trying out like some of these examples and trying to find the pattern that could cover the situation. But where you guys are going from top bottom is definitely the goal here. But I don't want to give the solution to this one. I feel like you guys can definitely work on it as a team and get to it. But that's what we need to figure out here. How do you do that? And something that may help clear out all these options, clear out everything we thought about, and start from scratch again. Like we said,
I agree.
Go back to the heart of the question.
Yep.
We might be starting to pigeonhole ourselves into a certain approach. So you know what? Even ignore what I said, maybe. Someone else has been thinking of something but hasn't said anything. Bring it up. Say, I just want to try this just for the fun of it. And what can happen sometimes is, while your test may not give us the solution, it could expose us to more hidden information. I've gone through trials of this stuff, of certain algorithms. I've tried an approach, didn't give me my solution, but showed me something else different about the data, how the data works and how the information connects to each other. That gave me the ending, that resulted in giving me the solution I wanted. If that makes sense. So no, if your approach seems weird and even if you're not confident, it would definitely give the answer in all scenarios. Walk through you can definitely still go through the approach and do some tests on it, because with some extra eyes, you'll be able to tweak the approach and find the actual solution. So if someone else has a process, go with it. I was the only thing I did with you guys was just to point out again, it's dangerous to start from the bottom because of how large the numbers are, especially if we're making singular increments. That's all we're saying. If you can start from the bottom and make larger increments, then that can be fine. The main thing is just making sure we're not going one by one by one in any of the approaches we go by. We have way too large numbers to do single increments. That was the main focus of what I was trying to point out with like Alita and Evan's approach. But could there be a way to go with Evan and Alita's approach? If let's say we start with 1, 2, and 3, but then we take 3 and go all the way up to the maximum value we can, and then take 2 and go with that up to the next maximum value we can get to, and so forth and so forth. Could that have maybe worked? I never said that Alita and Evan were in the wrong scenario. I just said that their approach of going one by one by one, that was dangerous. So maybe try that quick right now, just for the fun of it. Yeah, let's do that quick. I'm gonna give you guys this a little bit. So take that 1, 2, 3 that you guys came up with the low numbers. But then think about, can we jump any of these numbers? Well, we want to get to 12. We have 8. We have boxes up to 8. let's start with 3. What's the highest number we can take 3 to? That would still work with 1 and 2.
Oh,
The highest number we can go to.
we can go to 8.
We can go to 8, no, 8, 9, 10, 11. Oh yeah, we could do that. So yeah, that's is within,
Mhm.
right? So if we take 3, change it to 8 with 1 and 2, we're still under our goal, right?
Mhm.
So let's try that. Now let's take our 2. Can our 2 go up to something that will then give us 12?
Yeah, we can jump 2 to +1 and that will give us our goal, right?
That was really fast, wasn't it?
Yep.
Play with this. I'm going quiet again. Play, earn, we said last time. Once you find something that has potential, build your confidence in it. Try to, now what your goal now to do is to try to disprove this. To say, can we find a way for making sure that this does not work? Find a way to say this does not work or it's going to take us too long to use it. Increase the number of boxes you need. Do the higher numbers if you think that'll help. But now that we have something that seems like, ooh, we were able to find a solution with this concept, can we break it now? And that's going to tell you whether or not something that gives you confidence whether or not to build that. I'm going to go quiet again. Again, have fun with the annotations. If someone wants to clear up some of those annotations up there, go ahead. So I know you have a lot of annotations up there right now that probably are a bit old. So if it's your annotation, you can, on your bar that's up there, there's a little garbage bin. You can click on that and delete all your drawings if you want, by selecting clear all my drawings. So.
Yeah, just before you do there, you know, the top right is Alita's increment by 1, start at the bottom, increment by 1, and the bottom left is Cliff's. Yes, start at the bottom, but find a different way to increment.
Right, don't increment by 1, increment large, jump more, make larger jumps, because we're not dealing with arrays or sequences necessarily. That was my only issue I had really with Evans and Alita's approaches, was this increment by 1 situation. Because again, I pointed out we have a 1 quadrillion or 100 quadrillion as our maximum number. So we can't be doing +1s. But no one said you couldn't take the current highest number in our set and jump that up as much as we can, then take the next one. Because right now, by doing this, we've put the restriction that we have the B boxes, right? Is that the number, right? Yeah, we have B boxes. Now we just need to make sure that those B boxes can be moved into a way that'll get us the number we want.
Yeah, and that's
Right.
what I'm kind of like questioning though, because I already know that if I just jump that up to 1, I can make it, but the computer does not necessarily know that. So
How would we tell?
yeah,
That's
and
it.
if I
Hold
jump,
on.
if I went
Why
to,
did we know we could? So let's argue that. How do we know we could have moved this to 8? How do we know we could change 3 to 8?
because adding all 3 of them, adding all 3 would be 5, but
Nope. Adding all 3 gives us what?
6.
11.
6.
Yeah, 6.
3, 4, 5, 6. We know that 8's our maximum, but we also don't want to count the 3. So we have to say, because we're not going to count the 3 anymore, right? We're actually going to say, okay, well, we have 3. I need 12. So I need 9 extra. But what's my best number I have for 1
8.
box?
Is an 8.
I have my 8, so I can take the 8. So this is the argument. How do I teach the computer to make that decision? So that's what I think that's what you're trying to say. You were able to very easily say, well, I know I can take the 8, but how do we help the computer to make that decision? That I can grab the 8 here, but on the second change where we change the 2, how do we know not to jump to 7? Or how do we know that the 2 should go to 3?
Yeah.
How do we teach the computer to make those decisions?
And
that's what you're going to justify now.
Yeah, that's my question, because we know that we could take the largest number because we don't have that, so we could easily say we could take the largest number and put it in. But instead of just trying to increment by 1 to be able to figure it out, how do you know?
And so for me, what I would argue is the best way to find out what that logic is, how do we teach the computer to do something, is to run through more examples and start bringing it down to more simpler phrases that are more we know how computers think. We know what items we have available, and think about the variables and the values we have available. So that's when it can help now to start bringing up what we have, as what John mentioned in the solutions, what do we have? We have that n equals 12 in this one. We have the b equals 3. We have k equals 8. So these are numbers we know we have, and we can always, so we can use those. We know we have the ability to add more variables or more memory points or more tracking items, things to track with. So once we have an approach that's human-wise, now we just got to see, okay, how we break this down into computational logic, right? So now start working through that. And again, the best way to do that sometimes is to adjust your test case and walk through them. So go back to the like in here, go some more, pull up some more of the sample cases, walk through them, walk through the decision process. And the more items you go through, you might start making the realization of what are we asking? What should the computer be asking? We know, and because we know this one has a valid solution, and these two both have a valid solution. Well, one of them do, because it's really only one. We don't care. We know this one doesn't have a valid solution. So how can we know that this thing can tell us we don't have a valid solution? So those are the things you want to start thinking of now as a team. Start working through some until you know what the logic is that we need to tell the computer, and you can write pseudocode. But again, I'm gonna go quiet, let you guys work with this. But I gave you guys something that you can at least play with and try to figure it out. So now as a team, so again, ask that question in class. Someone, you don't have to have the answer. Be like, here's how I think we could try. Let's try this. All right, go for it.
Well, if we add 1, 2, 3 is 6, so we know we can't get to 10 even because we're using all the numbers. So that turns out to be a -1 because you can only use 3 and the maximum number is 3. So that one we already know.
Let's try a new test case.
Yeah, the 10 and the 9 and the 2.
Hold on. Before you say that, James, you really haven't explained exactly how we know, or Jim. I don't like how you James for some reason sometimes. But go through the logic we have and try to see, with the logic we have, can we prove that it's invalid instead of just saying we know it is because of this and this.
Well,
so we have this. Whoa, where did that come from?
No, my thing is you've got 3 numbers. You can only use 3 numbers, and your number can only go 1 up to 3. Wow.
Well, again, use visuals so that people can see it. It's one thing for you to say, but help people see how we know we can't.
Okay, so.
And then try to change it a bit to see if we can still determine it. So, and I'll explain what I mean in a second. So yeah, you have the touch screen. So I'm gonna let you draw this time.
Yeah, so n equals.
Oh, why did they give you the brown? Oh, that's
bad.
Oh God, no! I'm just disgusted looking at it. Sorry.
That was just default color that gave me to me.
I know.
I have a nice light gray.
Everyone picks a color for you.
90% transparent.
Right, you want me to do this? Is this good here? How about black?
Sure.
Wait,
it might be too dark.
Oh wait, I need to draw.
Red. Go red.
Red.
Red sounds good.
Yeah, red.
Right one.
Brown. I cannot help but get disgusted by it. I don't know.
Is that good in color?
Yeah, I can see.
Okay, so then
you can read that. The brown was not readable.
Yeah,
legible.
And then we've got B equals 3 and A equals 3. So then we can only do 1, 2, 3.
Mm-hmm.
And so if we add all these up here, then we get a 6.
We know we're not there, and when we ask, can we increase 3 to anything? We know what?
We can't because 3 is the maximum.
So that's one thing that tells us how. That's going to tell us, okay, can't do it. We can't increase our number 3.
Right.
Let's do a little different here. Let's change our K to 5. I don't think that'll give us. I don't think that's valuable. So we now have a maximum value of 5. We have 1, 2, 3, 4, and 5 as our boxes. Wait, that might work. Shit, nope, that'll work. I just realized in my head that there's a collection for that.
So you can do a 4
n to 15. Change n to 15. No, K5 and 15. Yep.
Okay. Okay, so and then
K is 5.
K is 5.
Yep. So now we want to be able to prove that we can't get there. No, we still have only B3. Hold on.
We're still, oh, okay, right.
We're in
right,
B3, so we can only have 3 boxes. So
Okay. So,
we know 1, 2, 3 equals 6, so that's not valid. So what can we do with the 3?
oh. Well, oh, K equals, wait. Oh, okay, K equals 5. So
Mhm.
we can jump the 3
Mhm.
to 5.
Yep,
So that would
we do
be,
that.
so that would be,
And then someone else do the math real quick. What would that total?
8.
Now it doesn't work, right? Let's go to the next number, 2. What can we do 2 now?
two.
To 6.
Well, we could go to this one to 4 because it would be the highest, right? Next
That's the
highest.
highest number we have it. Yep.
That gives us 9.
What is that?
That the 10. That
Still
gives
not
us.
good enough.
Yep.
Right. Yep, that's 10. Not good enough still. Can we do anything with the 1?
1. We can go with the highest of that to 3. To
3.
Yeah.
3.
And that gives us
Well,
12.
12. And we've changed everything we can change, right? So is that a way we can now say, we can now confirm without a shadow of a doubt that this can't be made. We can't do 15, right?
Right.
So we've now found a way of at least logically proving we can't get a number potentially, right? If we go through all our boxes, raise all our boxes to its maximal possible value, and we can't get it, then that proves it can't be done. So that's one way of doing it, right? There we go. And we didn't have to iterate through all the numbers, did we? Our O was the length of our O was O of like, what is it? K, not K, B. Our O was O of B. However many boxes we need, that's how many iterations we had to do, right?
Yeah, so we did 3.
Yep. So again, play with this more. People, make sure it makes sense what we're trying to do here, what we're playing with. So play around with it a little more. I'm gonna go silent again. I feel like your approach is right here, but play with it until everyone here understands it. So if there's something you don't understand, try to come up with a test case around what you think won't work. So make your own test case, like, you know what, I don't think it'll work with this scenario. And prove whether or not it will or won't, all right? Until you know the confidence in it. And again, the goal here is until we can figure out what the process is. So the logic, how can we make sure that the system knows what decisions to make? So think about when we do these things here, listen and pay attention to the questions. So I'm gonna go quiet again. I want you guys to work it. I don't want to give too much, so I'm going quiet. And now that you guys have more examples, I'm gonna delete my code again. So on my drawings, you have more room to draw.
All right, so I'm coming in late. So the question is, he wants to buy a specific amount of sticks, which is N of spaghetti, right? And K is the sequential number of boxes and how many sticks of spaghetti are in it.
It's the number of boxes in the store, and like each box has a certain number of sticks, and it ranges
Right.
from 1 stick to 2 sticks, and they all have unique number of sticks.
Right. So box number 1 only has 1 stick in it. Box number 5 has 5 sticks in it, right?
Yeah, and it goes until K and including K.
So do we have to return numbers of 3? Is that what I'm understanding? Or arrays of 3? Or
No, that's how many boxes you need to buy.
That's the test case that they're running through right now. They're setting B to 3. So remember, B is the number of boxes we want to buy. So you could set B to 4, 5, 6. So you could do more, where they just currently when you jumped in, that was the examples you were doing, because a lot of the test cases did B3.
Okay.
So
Technically, you can have a B of what is that? 10 to the 5th power. That would be what, 1,000 boxes?
Yeah.
So 10,000 boxes. I don't know. Unless someone here thinks they have the logic. If you think you do, walk us through that logic. Take a test case and say, here's how I think the logic works, and walk us through it if you think you have it. But that's it. Someone either walk us through if you think you have the logic, or if you don't, postulate a test case, and as a class, work through it with the current logic we think we have.
Well, considering, shouldn't we go through it backwards? Because you want the highest numbers and then add from there? Because that's what it looks like in that example, 842, 752, 761 for the possibilities.
Yeah, we're just looking for any possibility. They don't care which one it is as long as it's a valid option.
Well, that's what I would do. I would go through it backwards, only because once you have the highest number, then you would just have to figure out from that highest number how to make the other combinations. So in other words, you find the highest number. So on that one, it's 12. So the highest number was 8. So then from there, from 8, you can use whatever combinations. Then you know it has to be 3 numbers that add up to the final number, because that's B, right?
Yeah, but
Again, work through examples to make sure that that works.
yeah, see, the thing about it is though, if we do this one here where n equals 9, b equals 10,
Yeah.
and k equals 2. Is that how it is? Is that right?
No, I think,
Well, that wouldn't be possible.
No. So it's gonna be b equals 2. B equals 2. K is 10.
yeah, that's right.
So we can't use the highest number because it's greater than n. And we
Yeah,
can't.
obviously. What I mean,
and
the
we
highest
can't-
number,
Well, I know this is the thing though. If we went with the highest
number
we-
that's less than n. Sorry.
Yeah, but we can't even use n because we would just have to keep going down. Well, the next one would be 8. And
Right.
you
So
can only
that's
use,
supposed to be 8.
2 boxes. You can only use 2 boxes in this one.
Why not?
What?
Because you want 2 boxes, so it would be 8, and then the other one would be 1, because K goes from 1 to 10. Right? If you think about it logically, if you went backwards, you can't use 9 because it's not 2 boxes. You could use 8. So 8 plus 1 equals 9. 7 plus 2 would equal 9.
Yep.
6 plus 3 would equal 9.
So, but if we did it this way.
Just a thought. I'm just thinking out loud.
If we just start with 1 and 2, we could change that 2. We could change that 2. We know 10 wouldn't work. We knew 9 wouldn't work. The next one would be 8, and then it would be done.
That's what David said.
Yeah, I was
you're
afraid
just
that
going
example was
forward,
actually not going to be
going
great.
backwards.
I was afraid that example was not going to be great. The better example would have been the 12-8-4.
12-8-3?
So go 12-8-4. No, 12-8-4. N12, B3, K8. Sorry, B4, K8. That's kind of the best example for showing that it can be a little dangerous by just instantly always taking the highest possible. And you'll see why when you go through that one.
What was those numbers again?
N12, B4, K8. So start with the largest, we have 8. We still need 3.
Oh. This one we need, why is this not erasing? So B would be 4, so we need 2 more spots.
3 more spots.
Oh, yeah.
Yes,
No,
it
but
can't
no-
work because you need 3 more boxes to add up to 4. And the best you can do is 3 boxes to add up to 6. So already you know that can't work with 8.
Yeah, that's true.
So now,
Lowest.
now that we've proven that this just instantly grabbing the biggest is a difficult item, let's do the one we did before. We do the already existing collection. 1, 2, 3, and 4. We have those. What does that equal?
10.
3,
equals
6,
10 now, right?
10.
10. So where's the maximum we can go with 4 if we're trying to equal 12? What's the maximum we can bring 4 up to?
6.
Right, and is that, so it's 6, 3, 2, 1. Is that a valid option?
Yep.
Yeah.
Done, right?
Well,
That's what I'm
that's what-
saying. Come up with different scenarios to test these things. Which, yes, it's agreed that we can't always grab the super max because we have this thing where we need a certain number of boxes minimum, and we can't use duplicates. But we still want to always try to get the largest possible. And that's what I wanted to be very clear on that, and that's what I was trying to clarify. You, with again, where I saw with, was it Evans and Alita's solution going 1 by 1, that doesn't work. But again, also grabbing just the largest every single time doesn't always work either. We want to always grab the largest possible. We need to understand, we have to have a minimum number of boxes. So this is where this system here helps. We already have 4 boxes or 4 items collected. Now we're just swapping out boxes with others to see if we can hit our value. Does that make sense?
Mm-hmm.
Well, yeah, that's why the 9, 10, 2 work, because if we started with 1 and 2, we would have to, we could determine the first 2 highest numbers are not going to work, and we wouldn't need to change the 1 because when we hit the 8, it would.
Exactly. Which is what we just did here on this one. We only
Yeah.
increased the big one 4 to 6 and we got what we wanted. Same thing here. We would increase the 2 to the 8 and we'd get what we want.
Yeah.
So again, figure out this logic of how to make this thing work. This is, I feel like, I think some of you guys may be feeling confident that this is our solution, but now you have to come up with the actual logic for the approach, right? So we have an approach. We have a human way approach of doing this. We have the numbers we have our starting values. Now we just need to know what is the logic to change each of these numbers to the number we want, right? Go for it. You guys can do it. And again, if you want, just for fun again, and for some of you who still don't feel this is confident, instead of going right to left, because some of you don't like right to left with arrays, let's try going left to right with this. So we have a 1, 2, 3, 4. We are at 10. Can we increase our 1 to something that we can use?
4 equals 10. Yep. Oh wait, no.
Can? No, right? We could
No.
increase it to 3, but 3 is already taken, right?
Yeah.
We can't do that. We go to the 2. Can we increase that one?
Increase 2.
No, well,
No.
we couldn't.
Because again, that would go to 4. It wouldn't.
Yeah.
Let's increase the
We
3.
already
Can we
have
increase
4.
the 3?
If we put that to a 5.
Yeah, that would work, wouldn't it? And there we go. We have another way. So there's multiple ways to tackle this. So try to find what works best for you guys. Go through a couple examples, change things up until you feel confident in the approach and you know what the logic is. That's what you guys want to do now. And I want to hear more people just throwing things out, saying, you know, I want to drive the annotation for a little bit. Throw out some options. Jump in here if you think you have it. Again, this is mob sessions. No one should be coding this alone. Work it, work it.
I think I'm gonna get rid of my n divided by b.
Okay. Yeah, some people.
That was a rabbit hole.
Yeah.
Good thing we didn't go too far in that.
The approach was nice. I was just curious to see how you. I actually didn't have any. I couldn't tell if that would or wouldn't work myself. I wasn't sure. I liked the idea. I couldn't tell if it was good or not.
I got the idea from you. I was going to start at the biggest number, keep dividing by 2 somehow until
Yeah.
You've taken in some
Um,
requirements. So that was a general idea over there. But this approach is real nice.
Yes.
Can I interject?
Go for it, Christian.
The logic of trying to solve it's kind of confusing me, but I think I came up with the 3 possible fail cases. And
Let's walk.
because if we find out the fail cases, then we can just work on the logic of actually, because we know things will work. That being the case, or at least the assumption that's confident, if you're in your code, you can find a solution to work, how to code the logic out.
Go through it.
How did Cliff, John, how do you guys feel about that being a step forward before trying to figure out the logic to actually
Go through
create
it.
the
Yeah.
return list? Yeah.
Go for it. I'm curious. Go for it. I want to see that.
So, here we go. I'm trying to draw on the screen. They're kind of just, let me just say them, and then if we need to draw them out, then I will. But because I put them into like just worded form. So, okay. So if that array, how Alita and everyone we're talking about, or actually everyone we've been talking about, is it's gonna be from 1 to k. You know, that's what we've been working with so far, like that 1, 2, 3, and all the examples, and then we were like swapping the
Technically
same.
starts at 1 through B, doesn't it?
I thought it was 1 through k.
Like what we have
Oh
here
no,
on
that's what I
the
meant.
on
1 through
this.
b.
Okay, yeah.
Yes.
I was making sure.
1 through b.
Okay, cool. I thought that's what you're talking about. I just want to make.
Yeah, so if it's 1 through b, that's the initial array that we're starting out with. If that value, which, and this is what Cliff was saying, was, could be tough if it's a huge amount. If that value is greater than n, it's automatically gonna fail. Because that means
That's a good
we
way of putting it.
can't.
Yeah.
And then another one is if k so if k summed all the way up to k minus whatever k minus b is, so let's just say k is 5 and b is 3. That's awful. I don't know, k is 7 and b is 6. So if, okay, I gotta word this. A,
How do I get?
Less than n.
Christian, would that be a good way of explaining your rule 1, your fail case 1?
That wouldn't, I don't think that would be the fail case 1, because that way we're still.
Well, the thing you just explained, if the sum of 1 to b is greater than n, fail.
Well, okay, yeah,
Right?
that's
Yeah.
that's true. Oh, well, actually, the first fail case I think should be if n is less than b, fail automatically. So I think that is actually exactly same thing I just said.
N is less than b. Wait. If n is
So-
less than the number of boxes. Oh yeah. That
Yeah,
would fail.
so
wouldn't it?
because that would automatically fail.
Yeah.
You can't fit that into the array. And then if that doesn't fail, maybe then check if
The
sum
initial
of
the initial
1 to
selection.
b is too big. And then this other one, I'm trying to figure out how I worded it. I think I wrote it too quick, but it says if k summed up from k minus b. So if k minus b is 3 and k is 8, 3 plus 4 plus 5 plus 6 plus 7 plus 8, if that summed up is less than n, because that's starting at like the largest amount to the lowest possible amount that can fill our initial array. Like, as an example, if none of the ones that they gave us for the sample failed, do they?
I think what you're trying to say is this
Yeah,
case
second one
would
fails.
be. Oh, I think the other one is if k minus. Yeah. God dang it. Hold on. I think I know what you're trying to clarify.
I can
If
write it out. I'll write it out.
the sum of K and K minus B is
Yes.
less than N,
Is less than
fail.
N, then it fails.
which is what we
because
did
it-
in our 10-3-3 example. Remember
Okay.
that? Or 10, or technically our 15-3-5, right? We did
Okay,
that 15
because if you,
5-3 version, which we went from 1, 2, 3. We ended up at 5, 4, 3, and we couldn't equal 15, right?
Yeah.
So that's our K and K minus B.
Yep.
Kind of.
so I was just saying, do all those three first. If any of those fail,
But you could check, yeah. You could definitely do those
Yeah.
first, yeah.
I don't know
You
if
don't
there's
have to
any-
then go to that point. Yeah.
Yeah, we wouldn't even.
That could be a quick,
focus on
and that's actually really interesting. A quick fail something too. Yeah, good, interesting approach there. If the three B largest items are less than N, fail it instantly. That actually would work. Yeah, we
So that
got
would
the
just-
B
those
largest
were-
boxes, and that doesn't hit our goal. All right, that's a good actually. Yeah, I didn't think of that as another quick fail.
So
I'm sure there's other ones, but for those are three that I thought would in case, and I tested it out really with a few different test cases from the whole thing and did the math for them, and a bunch of different ones with a bunch of random numbers were all fitting into one of these categories for failure.
So
not that
some of the
not
top
that it's
B,
going to hit them all, but one of them is going to hit for one of these are always true for any of the failed cases that I found.
I was working on the failed cases, and the first thought I did was just run the total of all the numbers up and then see if it is.
Again, we couldn't do that because we have 10 to the 18th power.
Well, let me finish. I did
Okay,
that. I did that, and I found it to be, and then I did think, well, what if I had like a million numbers or whatever? So I simplified it down to if K is less than N, and if B is greater than or is less than or equal to K, then fail. And I found most of the failed cases actually failed. There was a few of them that still didn't work out right, but I found that kind of worked for majority of the cases that would fail, and they turned out to be failed. So I think that
Okay.
Christians. So I think that because Christians has like the sum of all of them, or what the sum of what was the sum?
So some of the smallest three, the smallest B. So these are the smallest B.
Yeah.
If that's greater than our goal, we already failed because that means we've just grabbed the smallest boxes we could
Yeah.
of B, and we're already over our goal. We can't grab any smaller boxes, so that fails it.
Yeah.
And then we can also do a quick test if we grab the B largest boxes, and that puts us less than our N, meaning we don't even reach N, even though we grabbed all the largest boxes. That's an instant fail too.
Yeah. So like I said, mine did kind of work with for a lot of them. Like if K is less than N, and B is less than or equal to K, that failed.
Now I think we're focusing too much on the fails again. We still need to figure out. So
Yeah.
it's not a bad thing that we can figure out the instant fails that could save us some processing. But I'm almost to the point. I actually tend to worry about those technically later after I find my logic, because those are ways to just speed up the process. In most cases, your process should be able to also detect failures technically, because in most cases that's how it works. But yeah. Instant failures are a great way to speed up the performance of an algorithm. But and again, this is just my personal, how my brain works. Determining the instant fails, I don't think has ever led me to a solution personally. But again, I just haven't run into that situation yet. I'm not saying it can't, but for me, it hasn't. I still need, so yeah, if I don't instant fail, I'm still at square one now though. Yeah, I figured out I can easily kill off any invalidations with some quick fails, but I still need to figure out the actual answer still. I'm kind of still in my same situation, right?
Yeah.
Oh, yeah.
And that's where my thought came into play, because I don't know if I'm the opposite of you, but I tend to, I don't know. I like.
Hey, if it leads you to the solution, I don't mind. I'm just, yeah.
Yeah. I think because not that these are all the possible ones there are, but if this is the case, then what we code for logic, we know we're working with possibly valid data that can be a result. So with that being the case, I thought in the whole idea that we were doing where we were creating the initial array and then putting the largest number in and then keep doing that all the way down would validly work, because you would start and you would fill the array, and then if it, you would come to a point where you can now fill this with the correct amount of numbers that would work, and you could return it.
Yep.
That,
For
and to
me,
do,
these two I love. These two would be great ways to easily fail or solve something that would actually save time. I feel like number 3 is kind of our end case. When we finally gone through all of our logic, we will end up at this condition as a way of saying, okay, we've gone through all options. We can't do it. It's failed.
Okay.
I wouldn't put this as an if statement in the beginning, because then we're building 2 arrays now with these 2 right here, and doing the sum method on both of those. So I do think the first 2 instant fails are something that probably should go in our code, but that third fail, I think that third fail is something where we will just happen upon as we go through this current logic we have, once we figure out the process for it, once we figure out the computational, or once we figure out the instructions. So that's what we need to be working on now. How do we do these instructions where we tell the system to do this? What we've done before. And again, if it helps you guys to walk through a couple more examples, do that until you know what the if statements are and what the flow is. Work through it. And if anyone wants to be the one to walk us through another sample case with this logic that we have here, volunteer and just say I'm writing stuff. Well, yeah, can we clear out your code or your drawings? And I think, Evan, these are still yours over here. Can you clear these out too?
And the yellow.
Oh yeah, the yellow is you too, isn't it?
Yep.
I forgot that was the first stuff you drew. That's been here since the beginning. That's just gonna be a big blob on our screen from the very beginning of the video.
So,
Alita, are you able to remove yours? I just want to clean up some space.
Yeah, I went to remove it earlier, and then I felt like I accidentally deleted yours. Let's see.
I don't think you can. Yeah, you can't delete mine. I probably ended up trying to delete mine as you were deleting yours. So.
Oh, okay. Do I just do clear?
As long as the option says clear my drawings. I don't know if you have the clear all drawings option.
It's only just clear your.
Yeah.
I think
I
only
clear my
the-
drawings.
I'll do eraser. Let me try it out now.
You can hit the clear. If I have to rewrite it, I'll rewrite it.
I got it. Cool.
So the thing about this, about the way we're doing this one, of what numbers of we're doing the way we're currently thinking about having the 4 slots and then swapping numbers and figuring it out, is that since we have multiple answers that we can have multiple answers. There's no one set answer. Some of them may have one answer, but most of them have multiples. So coding this could be any way we want. We could do the last one, the highest one, and go with that one, or the middle one, or the last one. Any of the ones we can change, because as long as we derive an answer that suits the
Like I
answer.
said, well, that's why I did that example where I showed in the first couple examples we went right to left on our array of B's, and then I also showed that we can go left to right to do it as well. We could try left to right as well. So there's definitely a couple ways to do this.
And the only other thing would be is how fast can you get to how many numbers you can increment quicker to get to derive the answer instead of trying to instead of minimizing the changing of numbers to get the answer quicker.
Yep. Which if anyone wants to argue that, technically in this example here we did the what was it? What was this one again? This is the 12.
I think that was
8,
12,
4.
8,
That was
4.
Yep, totally 4. We were able to figure out it in one shot with going from the right to left. It took us 3 iterations to go left to right. But again, that's just in this example. Maybe others could go faster. And that's something that, again, going through more examples might give you guys more confidence. It might help you to figure out what the actual pseudocode logic is. Or if you guys want to, start writing what you think the pseudocode is. And you can always fill it in as you go. And once you realize, okay, I don't know what the next pseudocode to write is, work through an example. So maybe do that. Start writing some pseudocode and you realize, yeah, I don't know what I should write. Then do another example. Maybe that should help.
Well, first we would need to, well, pseudocoding, we need to make a list. I don't like to use the word list because that's code, but
that's fine. Collection.
Yeah. There you go. Thank you. Collection. We have to build a collection with default values. Or with starting values, not default starting values. Either one could be with that.
And you can probably clarify what the starting values are. What are the starting values?
Well, that's interesting because it really depends on what the code is. Because I've looked at the other tests, I've looked at test cases. Some of them only have like one number in it. It doesn't have 1, 2, 3. It doesn't have. Some of them have only one. Some maybe have 2. So you would have to depend that on B. Yeah, B is the number of numbers. Yeah, so we would have to default it on B of how many numbers we need to start with.
Not just B, but what B? Someone else, like, come on, somebody will help. I don't want Jim to give me all the code. Somebody else help them. Come on, if someone else knows the answer, go for it. Try to give you guys some hints. What is our starting collection?
Default values.
It would be numbers up to B. It would be numbers in order up to B.
What's the first number we start with?
1.
1.
Right, 1 through B, right? That would be our starting value, 1 through B. Yeah, there you go. Because that'll give us the first B boxes we grab, right? As our initial selection. And that would give us this collection right here in our 1284 example. So that line of instruction here gives us this array right here, the 1, 2, 3, 4 array in our 1284 example. So what's next, people? Heck, Amelia, if you know, just start typing.
I guess you would add them, right? Once you have those numbers, you have to add them and compare them to.
Yeah, then we have this we had these 2 initial failure cases, right? We have 2 initial fail cases that we could check for, maybe. And one of them does include a collection of 1 to B, doesn't it? Yeah, go ahead and say that again, Elaine.
Add the numbers. 1 to B.
In collection, I would say.
So. And then if it's greater than N, it's a fail. I'm going with the second one because I don't remember what the first one is. If N is less than B, we'd put that somewhere else.
That's good. Keep going that. Keep going that first. Let them finish that line. Because then we have, so that's one if statement. If it's greater than B, then N, we fail. So that would be, yeah, we know. Again, this is where we can use something. What's fail mean?
-1.
There you go. What's another scenario? So the list could be greater than, what's another scenario?
It could be if it's less than.
True, but that one probably needs more stuff. What's the other scenario, just in case? So then you can write that because we are going to need that. Keep that there. So if it's less than, that is a scenario we are going to have to deal with. But then I want to also make sure we have all our scenarios written so we can decide which one we want to tackle next. What's the other scenario?
The other scenario is if N is less than B.
Not that. So again, we have all the numbers in the collection. We added them together. We have if the sum of the collection is greater than N. We have if it's less than N. And then what's the third scenario?
It's equal to N.
What does that mean for us?
It's also a fail,
No,
isn't it?
that
Is
means
it
we hit
not
our
a
goal,
fail?
didn't it?
No, it would be,
Oh.
yeah.
That's what we want. Return collection, right?
Oh, yeah.
Yeah.
Wow. Oh, man.
That's what we're looking for. Remember that. So that could also be our condition as well for maybe a looping structure or something. But that's what we're looking for. We're looking to make our collection equal to n, the sum of our collection equal to n. But now, yes, if it's less than n, we have to do stuff now, right?
Yeah.
So less than n. There, he's gonna move it.
Yeah, buddy. So if it's less than n, then we're going to start changing a number.
Yeah, now we're gonna go through that process that we worked through, right? I want to clear up. No, that was my bad. I hit the wrong button. Undo. Yay. I just wanted to clear this stuff out of the way. There we go.
So we're going to then, what's the easiest way to do it? Let's start by changing 1. If it's less than n, if we
Yeah, now you guys want to discuss what is that process that we did with these items. Again, if you need to now work through a couple examples, remember what the flow is, go ahead.
It seems like it's like recursion, because you can try this, and if it doesn't work, we can scroll back to another number, then change another number, then go back, and then just keep.
I wouldn't say recursion. What's the better term for that?
I don't know.
Looping structure.
What is recursion? Thank you, looping structure. Remember, recursion is a looping structure. So don't just jump to recursion, lead with looping structure, which leaves it open to say, yes, we could use recursion, but we can also just use an if, a for loop or a while loop or a do while. It doesn't bind us to recursion. So always be careful with that. Using a term like recursion, just say, we need a loop.
Yeah, no. Well, I was thinking, because I was thinking as a tree, like you go down, you're trying out numbers, but then you can like go back up to the previous number and then try that, and then just keep going back and then keep going.
I would
forward.
clarify, yes, you can build a recursive solution to this, but I wouldn't recommend it.
Well, it seems like it's just as like almost like a tree, because I'm trying numbers, but if it doesn't work, then I could go back to the previous value, then try a new number, then if that works.
Recursion would be your way of, you would use recursion for a very, very brute force solution. I can tell you that as a seasoned developer. Using recursion in this would be used in a very, very brute forcey way.
That would be exponential time complexity.
Yeah, because you'd be trying every scenario. And then as you go through, you would then go back to try the next scenario. I wouldn't recommend it. But anyway.
At worst, anyway.
Listen, and we probably want to enable, we probably want to keep doing something until we hit our requirement, until we hit some scenarios. But yeah, anyway, keep going, building your pseudocode. I don't know if John has any tips for pseudocode here. But I'll let you guys keep working on it. Yeah, you're at the actual main part of the logic now.
So I think first you have to decide, are you starting at the 4 and changing the number, or are you starting at the 1 and changing the number? Like, I think you have to pick one or the other to start.
Makes sense.
So you guys, what do you want to do? You want to iterate from, do you want to start at 1 and add, or do you want to start at 4?
Let's start at 4.
Okay, we'll start at 4. So what we're going to look at, I forget how we did it. How we do it? We looked at the next number after 4, right? So 1, 2, 3, 4, it adds up to 10, and we're looking for 12. So if we make the 4 a 5.
Right, but how do we know which number to switch it to? I think we're gonna skipping a step.
Okay, yeah.
Well, you would want to change the 4 to the maximum number, providing that it's not greater than n.
No, greater than.
Yeah. And now that's what you're trying to figure out the logic. How do you figure out what the highest possible number is? What are the rules for that? So yes, you want to then change. Based on K, yeah, and your goal too. Remember how we noticed that we don't actually want to go all the way up to K. We wanted to go from 4 to 6. So remember, we have to take both K and N into consideration.
Right.
Think about that. That's what that's what you're trying to figure out the logic here is. What is the highest possible number we can switch our number to? So anyway, keep going. That's where the computational logic is. As a human, we can very quickly decide what our highest possible number is. I can just look at that, be like, oh, 1, 2, 3, 4 gets me 10. I want 12. I'm just going to move 4 to 6. I can do that very easily in my head without any rules, right? I don't need to consider any rules. I'm not doing any conditional statements or logic statements. I'm just doing quick and easy math in my head on autopilot. What now you're trying to do is take what I just did really fast, saying, oh, 1, 2, 3, 4 equals 10. I need 12. I just add 2 to 4. You need to break that down into rules that aren't using numbers specific, that aren't using this quick math that you're doing in your head. You need to actually break it down and figure out, how do I calculate that I should bring 4 up to 6, or technically K, and then move on to the next number. So we now need to decide that. How do you figure that out?
I'm thinking we take the sum of the values if they're less than n, then we subtract n from sum to figure out what we need left.
Oh, I like that.
And then we see if we can modify, in this case 4, or the largest value, which is b, if we can change this to make the sum equal to n. And if not, then we have to go lower.
Oh, yeah.
But going lower by 1 might be dangerous, so let's be careful of that. But need to break that down more though. Let's see. And I would call that difference. That would be another variable.
I was thinking like n is K. Well, I think there's an and statement in that if statement, meaning like one number is this, and as long as it's not larger than n.
If we add difference to b, and if it equals sum, we're done. But if not, we have to pick another number. I'm trying to break down that other stuff now.
So here's my breakdown. How did I know I needed to add 2 to 4? How did I know that?
Because our difference between sum and n would be 2 if we add these up.
And minus
Right.
the sum of the array is 2.
Yeah. Which, yeah, that n is not as wrong. Yeah, the sum of the array is minus, yeah, the goal minus the sum of the array gives us what we need, and that happened to be 2. And when I did the 4 plus 2, I noticed that that was less than K. It was a valid number, right?
Mm-hmm.
So that's what I'm giving you. That's my English for you. Convert that into pseudo.
Yeah, we determine the number and then we check that. Yeah, we determine the difference by doing, so yeah, we look at the sum of the array, and if it's not the, wait, sorry, we already saw, if it's equal to n, then we're good. Get the sum of the array, and then we take n minus the sum of the array to find the difference. Then
Up
we,
down to line 32, Emilio.
Yeah.
I think she's giving you what to type.
so yeah, the calculation to get the difference is, so yeah, calculate difference, and that's from n minus the sum of the array.
collection sum, or however you want to call it. Yeah, I think we did like sum. I don't know, however you want to word it. That works.
Yeah.
We technically called it collection, but yeah, whatever. We know what we know what it.
Mhm. Yeah. Then we add the difference to like the last element of the collection. So here it's 4. And yeah, and then we need to check. We check is this like new number we have, like that we just added the difference to the last element of the collection. Is this new sum less than or equal to k?
Well, I think it's safe to say that you can argue that the term difference is now a variable name, right? You could argue that. So you could say check if difference, or you could refer to that new total you got is called the difference.
Oh,
yeah.
yeah.
That's something to keep in mind. We can use that. When we say check if difference, we know that's referring to what we just did in the last line, because that word difference is there too.
Yeah, the last line just says add difference to the last.
Oh,
element.
whoops! I missed that line. I looked away for like a second. Whoops! My bad. Ignore me. For like a quick second because I heard Slack go off. Slack went off, so I missed line 33. My bad.
We'll just say like check if new sum is less than or equal to k.
The k or n?
K, because the sum that's in this like collection is referring to a box and how many sticks are in it. So in the collection we have like 1, 2, 3, and 4, and now we're gonna like say it's 1, 2, 3, and 6. And so,
Right, but if we add them up,
yeah, no, he's right. N. Sorry.
Yeah,
N.
You want to just check if you add them all up, you want to find it to be n.
Goal. Sorry. We really should change these probably to goal, boxes, or max and boxes.
When I
but it's fine.
When I said new sum, I was referring to like adding the difference to the last element.
Check if new collection sum. So I would say new collection sum.
Okay, yeah. But you also need to.
We're still.
Yeah, what are you saying?
Before you need to see like whether 6 is okay for us to do. Like, is there?
So maybe check.
True.
Yeah.
True.
I see what you're saying.
Yeah. That's what I'm trying to get at.
The line 33, hit enter.
Yeah. Okay.
Check if new number, right, or new element. How we want to call it.
If new element. Well, yeah. If new number
is less than k. Yeah.
If new number. Well, less than or equal to k, right?
Yeah, that's true. Yeah.
Yeah. Okay.
All right. Well, so yeah.
If yes, and if
you still want that line, except make it n. Yeah. Okay.
But now, what I would say, so line 35 is if 34 is true. Now, what if line 34 is false? What do we do?
Then we want to. Oh yeah, then we want to make the last element like the highest.
K.
Highest k as we can. Yeah.
We would make it k, because then what I would probably recommend doing is once you do that, you would change k, right, to 1 down. Once you set a value to k, we can reduce k.
Okay, yeah.
So line 36 would be if greater than k. Yeah, you guys figure out what's the best word. How do
35. We're doing the k comparison, not the n.
You got it. Yeah, if greater than k, set element to k. And k minus 1.
When you want to do this,
if you guys want to reword it, good. I'm not giving you guys perfect pseudocode here. I'm trying to make sure you guys do stuff.
K and k minus 1.
I'm saying like the steps of the logic are a little off. Like when you do before 35.
Sorry, what was
That's
that?
the thing. How do you handle if statements? How do you code if statements right? Because yeah, line 34 is an if statement. Line 35 is now what you do if line 34 is true. Line 36 is what you do if line 34 is false. So you got to figure out how you want to confirm those things. So I want you guys figure that.
Well, if you just want to keep the number if it doesn't check out right, you're just gonna leave that element there. If it's safe to use, then go ahead and change it.
Yeah.
And technically, what I would say, and I'm going to give you guys one more little hint. So I'm going to keep you from doing redundancies. Line 35. If line 34 is true that the new number was less than k or equal to k, we have now hit n, right? Because we got that new number because we tried to target n. So if that number we were given is given, we can just return that collection now. So line 35 should be return collection. We don't need to check if it's equal to n because we've already done that. We got that new number by doing n math, by trying to get it to n. So if that new number is allowed, we now have a valid collection. We don't need to test it again. So just get rid of the, return new collection, get rid of all that rest after on line 35. Remember, logical deductive reasonings. We got that new number through n math. If that number is allowed, we are at n. We can just assume that, right? Because that's what we needed. We needed that extra bit. We got it. We are allowed to use that. We have it. We have what we want. If not, we're going to set our number to k, reduce k by 1, and then move on to the next number in our collection, right? And I want to make sure that we're doing this here. Be very careful, Amelia, with this. This is a logic thing, true or false. I was just saying this is another line of code technically, but I wasn't giving you guys the actual lines. I don't know how you guys want to write that. So we want to set that last number to k, and then we want to reduce k by 1. Because we can no longer use that k box. That k box is available, so technically we now only have from 1 up to k minus 1. We don't have 1, but yeah, you get the point. Makes sense?
And then we would just go. And then don't we just
return?
Don't we just go back to 32 and just keep running this as a loop? Is it 30? Is it line 32 we start at to be able to?
Kind of. We do want to add the numbers in the collection again, though. Yeah, and we do want to make sure we add the numbers in the collection again. So we do need that. We kind of need, but yeah, you're right. We're technically at our loop. We do now want to. We're not going to repeat stuff. So again, let you guys figure out the pseudocode. But this is, you're pretty much almost there. What I might want to say actually is this might be a good spot to maybe even stop and let you guys try to figure out the final piece because there's some good pseudocode here. What I would say now, yeah, do this, Amelia. Line 36, go to the end, hit enter. Do repeat with next element. Another line. If I run out of elements, return -1. This should be what you need. So it's giving you definitely what you need. There's, again, pseudocode can't give you exactly everything. I want to make sure it's very, very clear. I don't want to keep holding down the space key. But pseudocode isn't going to give you the exact code. And what can be really good, I think that might be benefit to you guys is also tweaking the pseudocode a little bit to get more clearer pseudocode, or seeing if you can use this pseudocode to make the logic itself. So what I want to do now is challenge everyone to take this pseudocode, maybe clean it up, or just use it as is and write out the code now. This has everything you need, 100%. It's there. Is it perfect? No, but again, this is what a learning experience is for you guys. Learning pseudocode that makes sense to you, as that's going to help as well. So taking this, maybe adjusting it to pseudocode that makes more sense to you, or using, if it's this pseudocode works for you, then use it. But that's the next, I think that's going to be a good exercise for the weekend. And on Monday, we will review what you guys came up with. We'll take a look at everyone's code. We'll take a look at some pseudocode that you guys came up with. So what I would recommend is if you do change the pseudocode, save that pseudocode so we can also see what you changed it to. So some people can also learn better pseudocode techniques, because everyone here is learning this stuff. These are all things we're learning, and so that's the key. If you feel that if you adjust your pseudocode, save it so people can see, oh, that's an interesting way to approach if statements in pseudocode or conditionals in pseudocode. Oh, that's an interesting way to approach loops in pseudocode, right? That's one of the things I want to see here. And I may even challenge John to come up with his own pseudocode. How would he pseudocode this? Do you think you can do that, John? Do you have the time?
Right. Yeah.
Cool.
Yeah, it's really good.
Yeah, let's try that. So I'm gonna have you guys, So come either use the pseudocode as is, or you create or adjust it, and then write the code and see if you can come up with the code for this. You have the logic, it's all there, but that's gonna be due for Monday, all right? Sound good? Any questions? But yeah, I think this Thursday challenge is gonna be a good one. Getting these harder challenges is gonna really challenge you guys to really think deeper and really perfect your problem solving approaches. So I think, 100% on Thursdays, we're gonna be doing these harder algorithms to make sure you guys really bring down that problem solving process. Monday, we'll review these, and then we'll do a couple more of the 30 days of code, Tuesday, 30 days of code mob sessions, and then Thursdays, medium level hackering challenges. Sound good?
Mhm.
I think with this, we can definitely get you guys going in the 30-day window that we set.
All right, is somebody posting the pseudocode?
I just took
I was
a
gonna say,
screenshot of this.
Well, I
I was
will.
gonna say, Emilio, paste that to the Slack for us, please.
Yep.
So the 30-day window may still be feasible.
Can't we just finish 30 days of code too?
We're not there yet. I think we're day 21, weren't we?
Yeah, we're almost done with
Yeah, I
it
think we
too.
finished day 21. So we're almost done. So that's what I'm thinking. There's a good chance, there's a potential that we could finish it next week if we go well on them. So you guys usually solve around 4 to 5 a day when we do those. So it's within our capability and our power to actually complete 30 days of code next week, which would then allow us to do something different on Mondays and Tuesdays. We could do different mob algorithms on Monday and Tuesday instead. But until we do, we're going to do 30 days of code on Monday, Tuesday, medium level algorithms on Thursday. And then if we do solve those, me and John will work out some ideas of what we can do on Monday, Tuesday. Maybe do some more. We're really just going to, and the main focus is to kill your problem solving process for the algorithms. Because very soon, what I want to do the next week or the week after is maybe what we'll do actually, if we do solve the 30-day code, do 1 or 2 days of one-on-one coding sessions with me and John. We'll have you guys take a test of some kind. You'll go through a test on either HackerRank or LinkedIn, or do an algorithm one-on-one with me and John. Each of us will take one of you at a time. We'll go through the whole class. Does that sound interesting, John?
Yes, it does.
It'll be a different moment for you to be the one in the driver, to be the one in the reviewer seat.
Okay. All right, sounds good.
Oh, wait,
Yeah, so that'll be what happens. Yeah, we'll finish up 30 days of code. Once it finishes up, we'll do one-on-ones on Monday, Tuesday.
Hey, go.
All right,
good?
all right. I'm game for anything.
I know
I'll
it's,
see everyone on Monday. Ooh, what?
I said I know it's a slightly silly question, but I wanted to ask anyways. So doing one of the harder on the hard hacker ranks, I realize doing the pseudocode, doing what we do is it will work the same on a hard algorithm, but how much more work or how much harder is it to do a hard one versus the medium?
The main thing for the hard ones is you really got to take into consideration dynamic coding and your memory management and your time management. Those ones really want to take into those, and they also tend to have a lot more mathy kind of concepts, and they tend to also add in more pitfalls and more extra data. They're trying to confuse the hell out of you as well. So they're trying to make
more edge cases too.
Very hard to see. Yep. Oh, guys, that one too. A lot more. They do problems with a lot more edge cases, so it's very hard to get all of them solved. With hard algorithms, it's very plausible to get partial test cases solved, but it's very difficult to get them all solved because they're going to take memory management into consideration. They're going to take time complexity into consideration. And again, they're going to try to plant a lot of pitfalls, a lot of false data, and a lot of misleading information.
Okay.
They're going to, because in a lot of scenarios, you have that. One of the biggest issues that a lot of times we have in this era is the fact we have sometimes too much information, too much data. And so one of the things you have to do is kind of strip away from that. And that's one of the big things I like about this challenge, actually, this one specifically. There's a lot of fluff in it. We have papyrus, there's references to games, we're using spaghetti sticks. Elaine kind of pointed that out, how like, why sticks of spaghetti? What? And boxes of spaghetti with single sticks in them, and that just is insane. It's not a real scenario. So being able to pull away from that and kind of get away from that distracting information and just look at the core data is a key skill. That's why this one has that, because the medium level algorithm, they're trying to add in, I want to say like shiny objects. They're trying to add in shiny things to really distract you and pull you away from just the core level item. The algorithm with the solution is not overall that difficult, but it's hard to see amongst all the data, all the information, and all the fluff and all the pitfalls that are very much put in there. Like I said, the very easy pitfall that, again, two of you guys fell into was that concept of not realizing we can get up to a quadrillion on our number. So that was one of the big things I wanted to make sure that was a pitfall they purposely put there. So we couldn't do the factorial with addition instead of multiplication. That wouldn't work. That's going to be too much on the time complexity. So that was a pitfall they purposely put there because it's a medium algorithm.
Yeah, one of those test cases used like 100 million or something like that, because I was working on that one.
Yep, some of the numbers are high. Now, the overall number of items, the overall number of numbers you're using are not that large. You're probably only still doing like 100 boxes. So the overall numbers are like, the amount of numbers are not high, just the numbers themselves are high. So you have to be careful on that.
Those were negative one cases because the number was like 100 million, 1 and 1. I'm like, okay, well, that's not possible.
Yep. But again, one of the things they're doing is testing to make sure you're not doing that that quick checker you thought that might work, the summing from 1 to 1 to k, summing them all together and seeing if it's lower than n. Because that would, doing a 1 million 1 1, your error checker would not have caught it.
Well, it actually did, and it actually worked, but I didn't even go into a time complexity problem when I was adding all those numbers up. So
interesting.
Yeah, it was just a for loop, just adding them up. But anyways,
anyway, everyone have a good luck on this one. Go for it. If you do get to a point where you're completely stuck, do reach out for help, get attention, and remember, anytime, ping me. Sorry, Cullen, I missed your message earlier because I didn't see that one this morning, because I would have noticed that I didn't upload the video to the playlist. But I didn't see it. I didn't get added. So I was like, oh, I thought I uploaded all of them. No, I did not. So yeah, do not be afraid to at me if you need me. If I'm not at the computer and I'm about to be there, because I was literally I went to the corner store, so I was walking up through the apartment when Alita sent it. So I didn't catch hers because I was in the elevator, I think. But as soon as I sat down, I got Christians. I was like, oh, yep, I got it. I got to mention them. Didn't realize the time. So all good. Yeah, the videos are all up now. I'm going to try to get this one up as soon as I can. If you do not see it by tomorrow, just feel free to ping me. Let me know that I don't have it up yet, so I can get this one up as soon as possible. So anyone who needs to review it can review it. All right.
Okay.
I will see everybody on Monday. Have a good night. Have a good weekend.
Bye.
Bye.
Take care, everybody.
Good night.
Bye.
See you guys Monday.